Imagine the universe beginning with almost nothing. No stars, no planets, no galaxies, no atoms. Just an extremely hot, dense state filled with energy and the ingredients from which everything would eventually emerge. And yet, there is a strange problem. If the laws of physics treated matter and antimatter perfectly equally, the early universe should have produced almost equal amounts of both. Matter would meet antimatter. They would annihilate. Matter would disappear, antimatter would disappear, and what would remain? Radiation. A universe filled with light, but almost no matter. No Earth, no sun, no galaxies, and no one here to wonder about it. But that is not the universe we live in. Matter exists, and somehow a tiny excess of matter survived. That tiny imbalance became everything we see. Every star, every galaxy, every planet, every atom in your body. The remarkable part is that physicists do not yet know exactly why this happened. Somewhere in the earliest moments of cosmic history, something appears to have tipped the balance. Matter won, antimatter lost, and the entire visible universe may be the consequence of that microscopic victory. To understand how strange this really is, we first need to understand what matter actually means. When you look around a room, almost everything appears different. A table, a wall, a glass of water, your hand, a distant star. But at a deeper level, they are built from the same basic ingredients: atoms. Atoms contain a small central nucleus surrounded by electrons. The nucleus contains protons and neutrons are themselves made from even smaller particles called quarks. So the enormous variety of objects in the universe is built from a surprisingly small collection of fundamental particles. The electron is one of them. The up quark is another. The down quark is another. There are also particles such as neutrinos, photons, muons, and several others described by the standard model of particle physics. But there is an important feature hidden inside this particle world. Many particles have an opposite, an antiparticle. The electron has the positron. The positron has the same mass as the electron, but the opposite electric charge. The electron is negatively charged, the positron is positively charged. And this is not simply a particle with the wrong sign attached to it. It is a genuine counterpart predicted by quantum theory and observed in nature. The same idea applies to other particles. A quark has an antiquark. A muon has an antimuon. And even electrically neutral particles can have complicated relationships with their antiparticles. The existence of antimatter may sound exotic today, but its origin is deeply connected to one of the most successful theories in physics. In 1928, the British physicist Dirac was trying to combine quantum mechanics with Einstein's special theory of relativity. He developed an equation describing relativistic electrons. The mathematics produced something unexpected. The equation allowed solutions corresponding to particles with the same mass as the electron but opposite charge. At first, this looked like a mathematical problem, but Dirac eventually proposed that these solutions represented a new kind of particle, a particle that was the mirror counterpart of the electron. A few years later, in 1932, Carl Anderson detected the positron in cosmic rays. Antimatter had moved from mathematics into reality. And something even stranger followed. When matter and antimatter meet, they can annihilate. An electron and a positron can disappear as particles and produce photons. The matter has not simply vanished into nothing. Its energy has been transferred into other forms, consistent with the conservation of energy and momentum. Einstein's famous relation, E equals mc squared, helps explain why this can happen. Mass itself represents energy, so a particle and its antiparticle can transform their rest energy into radiation. This gives us a very important clue about the early universe. The universe was once much hotter than anything we can create today. At sufficiently high energies, particles and antiparticles can be produced from energy, and the reverse process can happen as well. Particles can annihilate and become other particles or radiation. Imagine this happening everywhere, not in one laboratory, not around one star, but throughout the entire young universe, a violent quantum furnace. particles appearing, antiparticles appearing, particles colliding, particles annihilating, energy becoming particles, particles becoming energy. The early universe was not a calm place. It was a rapidly changing sea of quantum processes. And at first, there is no obvious reason for matter to have the advantage. The known laws of particle physics generally treat particles and antiparticles in remarkably symmetric ways. If nature creates an electron, it knows how to create a positron. If nature creates a quark, it knows how to create an antiquark. So we arrive at the first great mystery. If the early universe produced matter and antimatter in almost equal quantities, why is there anything left today? This question becomes even more disturbing when we follow the universe backward. Today, the observable universe contains an enormous amount of matter. Stars are made of matter. Planets are made of matter. Interstellar gas is mostly matter. Our bodies are matter. Even the technology we use to study the universe is built from matter. Antimatter exists, but only in tiny amounts naturally, and we can produce it artificially in particle accelerators. The universe does not appear to contain vast regions of antimatter balancing our matter. If equal amounts of matter and antimatter had survived, we would expect something very different. Whenever matter met antimatter across enormous cosmic boundaries, annihilation would produce intense radiation. Astronomers have searched for this. They have not found evidence for large antimatter galaxies or enormous antimatter regions within the observable universe. So the universe seems overwhelmingly matter-dominated. But here is the remarkable part. It did not require much extra matter. The imbalance could have been incredibly small. Think of 1 billion matter particles. If the early universe produced roughly 1 billion antimatter particles alongside them, then having just one additional matter particle would be enough. One. That tiny excess could survive after almost everything else annihilated. The surviving particles would later become the material from which stars and galaxies formed. The numbers are astonishing. For approximately every billion antiparticles, there may have been about 1,000,000,001 particles of matter. The exact way we describe the asymmetry depends on which particles and epochs we are discussing. But the essential idea is this: the universe needed only a tiny imbalance, and that imbalance became everything. This means that almost all of the matter produced in the early universe may have been destroyed. What we see today could be the residue, the cosmic remainder, the small difference left after an enormous annihilation. Imagine two enormous armies facing each other. They are almost exactly equal. Then they collide. Almost everyone disappears. But if one side had even the slightest numerical advantage, that side would leave survivors. Now make the armies unimaginably large. Make the battlefield the entire universe. Make the collision happen when the universe is less than a second old. And make the surviving handful of particles the raw material for every galaxy that will ever form. That is roughly the scale of the mystery. But now another question appears. Where could that imbalance have come from? Because simply saying that matter was produced in slightly greater quantities is not enough. Physics demands an explanation. The universe cannot simply be told there were a few extra quarks. We need a physical mechanism capable of creating the asymmetry. And this is where the story becomes much deeper. The laws of physics contain symmetries. Symmetry is one of the most powerful ideas in modern physics. A symmetry means that something remains unchanged under a particular transformation. For example, the laws of physics do not care whether we perform an experiment here or move the entire experiment somewhere else. They do not suddenly change because the laboratory has moved across the room. More profound symmetries appear in quantum field theory. One particularly important idea is called charge conjugation. Very roughly, imagine replacing every particle with its antiparticle. Matter becomes antimatter, charges reverse. The question is, would the laws of physics look exactly the same? For many processes, they appear remarkably symmetric. But nature has already shown us something surprising. The symmetry is not perfect. There are processes in which matter and antimatter behave slightly differently, and that tiny imperfection may be one of the clues to the origin of the universe. To understand this, we need to travel into the strange world of unstable particles. Some particles do not live for long. They appear and decay. A particle can transform into several other particles, and the reverse process is not necessarily equally probable in every detail. In the 1960s, experiments involving neutral kaons revealed an unexpected violation of a symmetry called CP. CP combines two transformations. C changes particles into antiparticles. P reverses spatial coordinates, like looking at a process in a mirror. Physicists once hoped that the laws of nature might remain unchanged under this combined transformation. But experiments show that nature can distinguish between certain matter and antimatter processes. The discovery was so important that James Cronin and Phil Fitch received the 1980 Nobel Prize in Physics for their work on CP violation. This was not merely a technical detail. It showed that the universe does not always treat matter and antimatter as perfect mirror images. There is a crack in the symmetry. A tiny one. But perhaps the early universe needed only a tiny crack. The Standard Model later incorporated CP violation through the quark mixing framework developed by Makoto Kobayashi and Toshihide Masakawa. Their work explained how CP violation can arise among quarks. They were awarded the 2008 Nobel Prize in Physics. This gives us something extremely important. We know that nature can distinguish matter from antimatter. We know that CP symmetry can be violated. We know that the early universe contained enormous amounts of energy and particles. But there is still a problem. The amount of CP violation predicted by the Standard Model appears to be far too small to explain the enormous matter dominance of the universe. So the known physics gives us a piece of the answer, but apparently not the whole answer. And that is where the mystery begins to deepen. Because perhaps the universe did not merely need particles and antiparticles. It needed the right conditions. It needed a process capable of creating a difference between them. It needed a way for that difference to survive. And according to a set of conditions proposed by the Soviet physicist Andrei Sakharov in 1967, there are three essential ingredients for generating a matter-antimatter asymmetry from an initially symmetric universe. The first is that certain processes must violate baryon number. The second is that both C and CP symmetries must be violated. And the third is that the universe must have been out of thermal equilibrium. These conditions are now known as the Sakharov conditions. They do not tell us exactly what happened. They tell us what kind of physics would be needed. And each door opens another door. The first door asks, can matter actually be created in excess of antimatter through physical processes? The second asks, can nature treat matter and antimatter differently enough? And the third asks something surprisingly subtle. Why would the expanding universe ever fall out of equilibrium? To answer that, we need to go back to a time when the universe was so hot that the particles we know today did not yet behave as they do now. The familiar world had not fully emerged. There were no atoms, no nuclei, not even the familiar distinction between many of the forces that shape the universe today. The universe was hotter, denser, and more symmetric. As it expanded, it cooled, and something extraordinary happened during that cooling. Symmetries that once existed could become broken. This is not just a philosophical idea. It happens in ordinary physics. Imagine a perfectly upright pencil balanced on its tip. The situation is symmetric. There is no preferred direction. But the pencil cannot remain perfectly balanced forever. It falls. Once it falls, one particular direction has been selected. The underlying laws may still possess the symmetry, but the particular state of the system does not. This is the basic idea of spontaneous symmetry breaking. In the early universe, fields could occupy different states as conditions changed. The Higgs field is the most famous example. Today, the Higgs field has a non-zero value throughout space. Elementary particles interact with it, and this interaction contributes to their masses. But the early universe was hot enough that the behavior of the Higgs field was different. As the universe cooled, it underwent the electro-weak transition. The precise nature of this transition within the Standard Model is important. For the observed Higgs mass, it is not a strong first-order phase transition, but rather a smooth crossover. That detail matters, because some mechanisms of baryogenesis require a strong departure from equilibrium, and the Standard Model's electroweak physics does not appear to provide enough of it. So once again, we encounter a boundary. The Standard Model is extraordinarily successful. It predicts particles with astonishing accuracy. The Higgs boson was discovered at CERN in 2012, confirming a crucial part of the theory. Yet the same theory appears unable to explain why the universe contains so much more matter than antimatter. The theory works, but the universe seems to be asking for something beyond it. And perhaps that is the most interesting clue of all, because the mystery of matter may not be a problem about matter alone. It may be telling us that our current description of fundamental physics is incomplete.
There is something almost unsettling about this situation. We have a theory that describes the behavior of elementary particles with extraordinary precision. We have observed the Higgs boson. We have measured CP violation. We understand how matter and antimatter can be created and destroyed. We can reproduce many of the conditions of the early universe inside particle accelerators. And yet, when we ask the simplest question, why is there matter, we reach the edge of what the theory can explain. To see why, we need to look more carefully at one of the quantities that physicists use to keep track of matter: baryon number. A proton is a baryon. A neutron is a baryon. More precisely, baryons are particles made from 3 quarks, while antibaryons are made from 3 antiquarks. Physicists assign baryon number +1 to baryons and -1 to antibaryons. A proton has baryon number +1. An antiproton has -1. If a process produces a proton and an antiproton together, the total baryon number remains 0. That seems reasonable. And in many ordinary particle reactions, baryon number is effectively conserved. But here comes a remarkable possibility. Maybe baryon number is not an absolutely sacred quantity. Maybe the universe can create a little more baryon number than antibaryon number under the right conditions. If that happened in the early universe, it could leave behind the matter excess we observe today. But there is a catch. We have never observed ordinary laboratory processes that violate baryon number. Protons, for example, appear extraordinarily stable. Experiments have searched for proton decay because many theories beyond the Standard Model predict it. So far, no confirmed proton decay has been observed. That tells us something important. If baryon number was violated in the early universe, it may have happened under conditions that no longer exist. The universe itself may have been the only laboratory capable of performing the experiment, and that experiment happened billions of years before the first star existed. There's another subtlety. The early universe does not have to create a huge amount of matter from nothing. It only needs to create a tiny imbalance. Suppose there are billions upon billions of matter particles and almost the same number of antimatter particles. If the difference between them is extremely small, annihilation can remove almost everything, but not quite everything. The survivors become the matter we see today. This is why the asymmetry is sometimes described in terms of an excess of roughly 1 baryon per billion photons, with the precise value depending on the cosmological quantities and conventions being used. That number is tiny, but it is enough, and that tiny number contains an enormous amount of the universe's earliest history. We can actually infer the matter asymmetry from observations. The cosmic microwave background gives us a remarkably precise picture of the universe when it was about 380,000 years old. At that time, the universe had cooled enough for electrons and nuclei to combine into neutral atoms. Photons could finally travel freely over enormous distances. Those photons are still reaching us today. They form the cosmic microwave background, and hidden within its tiny temperature fluctuations is information about the density of matter in the young universe. The abundance of the light elements gives us another clue: hydrogen, helium, small amounts of deuterium, lithium. These elements were produced during the first few minutes of cosmic history through Big Bang nucleosynthesis. Their observed abundances provide an independent window into the early universe. Together, these observations tell us something extraordinary. The universe did not begin as an empty stage waiting for matter to appear much later. The ingredients for the matter-dominated cosmos were established extraordinarily early, and whatever produced the asymmetry had to happen before most of the ordinary structures we know had formed, long before the Earth, long before the Sun.
Long before the Milky Way became the galaxy we know today, perhaps before there were even protons and neutrons in their familiar form. This moves the mystery into a completely different era. The universe was expanding. It was cooling. Particles were interacting at enormous energies. And somewhere in that rapidly changing environment, matter gained an advantage. But why? One possibility begins with the particles that are among the strangest things we know: neutrinos. They barely interact with ordinary matter. Trillions of them pass through your body every second. Most travel straight through the Earth. For decades, physicists thought neutrinos had no mass. Then experiments showed otherwise. Neutrinos oscillate. A neutrino created in one flavor can later be detected as another flavor. That behavior requires differences in neutrino masses. So neutrinos are not massless. And once we learned that, another mystery appeared. Maybe neutrinos are connected to the matter asymmetry itself. This possibility leads us to leptogenesis. The word sounds complicated, but the basic idea is beautiful. Perhaps the universe first created an imbalance between leptons and antileptons. Later, known processes could partially convert that lepton asymmetry into a baryon asymmetry. Matter may therefore have survived because an earlier asymmetry was created in a different sector of particle physics. And one of the most intriguing candidates involves extremely heavy neutrinos that may have existed in the very early universe. These hypothetical particles are often called right-handed neutrinos or heavy Majorana neutrinos in particular versions of the idea. They would not be part of the standard model. They could be enormously heavier than the particles we know, and they could decay in slightly different ways into matter and antimatter. If those decays violated CP symmetry and occurred out of equilibrium, they could generate a lepton asymmetry. Then, electroweak processes could redistribute part of that asymmetry between leptons and baryons. The result could be a universe containing more matter than antimatter. Notice what has happened. We started with the question, why is there more matter than antimatter? And now the possible answer involves neutrinos that may have disappeared from the universe billions of years ago and may be far too heavy for our current accelerators to produce. We may never be able to create them directly, so how could we ever know whether they existed? This is one of the strange features of cosmology. Sometimes the universe's earliest moments leave fingerprints rather than fossils. We cannot travel backward. We cannot place a detector beside the Big Bang, but we can search for consequences, neutrino properties, cosmic background radiation, the abundance of elements, rare particle decays, the distribution of galaxies. Even the absence of certain observations can eliminate possible theories. The universe becomes a kind of crime scene, and we are trying to reconstruct an event that happened almost unimaginably long ago. But the neutrino idea becomes even more interesting when we ask a deeper question. Why are neutrinos so strange in the first place? For every particle we know, we can ask whether the particle and antiparticle are fundamentally different objects. For the electron, the answer is straightforward. The electron and positron carry opposite electric charges. But neutrinos carry no electric charge. So perhaps there is another possibility. Maybe the neutrino is its own antiparticle. A particle of this kind is called a Majorana particle, after the Italian physicist Ettore Majorana. If neutrinos are Majorana particles, then an extraordinary process might be possible. A nucleus could undergo a hypothetical process called neutrinoless double beta decay. Normally, certain nuclei can undergo double beta decay and emit 2 electrons along with 2 antineutrinos. But if neutrinos are their own antiparticles, there could be a process in which no neutrinos emerge. Only the electrons would be detected. That would be revolutionary. It would demonstrate that lepton number is not an exact conserved quantity. And it could provide a crucial clue about how a lepton asymmetry might have emerged in the early universe. Experiments around the world are searching for this extremely rare decay. So far, there has been no confirmed detection. Again, the mystery remains. But notice the chain of clues: matter-antimatter asymmetry, lepton asymmetry, neutrino masses, possible Majorana nature, possible lepton number violation, possible heavy neutrinos, possible connection to the earliest universe. These may seem like separate puzzles. They may not be. Perhaps they are different pieces of one much larger picture. And there is another reason neutrinos are especially interesting. They are connected to a question that seems almost philosophical, but is actually deeply physical. Why do particles have the properties they have? Why does the electron have the mass it does? Why are the quark masses arranged in such an unusual hierarchy? Why are neutrinos so much lighter than charged particles? Why are there 3 known generations of matter? The Standard Model tells us how these particles behave, but many of their numerical properties are simply measured. The theory takes them as inputs. It does not explain everything about why the numbers have those values. This is one reason physicists continue searching for deeper theories. And matter-antimatter asymmetry may be one of the strongest clues. Because if the universe contains matter only because some hidden physics once treated matter and antimatter differently, then that hidden physics must have left a trace somewhere. Perhaps in neutrinos, perhaps in quarks, perhaps in a new particle, perhaps in a new force, or perhaps in physics operating at energies so high that our current machines cannot reach them. This brings us to an important distinction. The Standard Model does contain CP violation. But the known amount appears insufficient to explain the cosmic asymmetry. That means we probably need additional CP violating physics. And whenever physicists hear the words new CP violation, they start looking in many places. One possibility is the Higgs sector. Perhaps there are additional Higgs-like fields. Perhaps the early universe underwent a stronger phase transition than the minimal Standard Model predicts. Perhaps new particles interacted with the Higgs field and produced an asymmetry during the electroweak era. This idea is called electroweak baryogenesis. It is attractive because it could, in principle, connect the origin of matter to physics near the electroweak scale. But again, the Standard Model by itself does not seem sufficient. The observed Higgs mass and measured properties indicate that the electroweak transition was a crossover rather than the strong first-order transition required by many simple versions of electroweak baryogenesis. So new physics would be needed, and that creates an exciting possibility. Maybe the answer is not hidden in the earliest imaginable moment of the universe. Maybe it is hidden in physics that we can actually test. If new particles or interactions exist near accessible energy scales, future experiments might reveal them. That is why searches at particle colliders matter. A collision lasting less than a billionth of a second could potentially tell us something about an imbalance created billions of years ago. The connection between laboratory physics and cosmology is astonishing. A detector on Earth can become a telescope aimed backward in time. But the universe has another trick. The particles involved in the asymmetry may have been extremely heavy, so heavy that the energy required to create them directly could be far beyond any realistic accelerator. If so, we need indirect evidence. This is where rare processes become important. Imagine a particle that is too heavy to produce.
you might still detect its influence. It could subtly change the probability of a rare decay. It could modify the behavior of known particles. It could alter the properties of the Higgs boson. It could contribute to neutrino masses. It could leave traces in cosmic radiation. The invisible can become visible through its consequences. That principle has already transformed physics many times. Neptune was predicted because something seemed to be perturbing Uranus. The existence of neutrinos was proposed because energy and momentum appeared to be missing from radioactive decay. The Higgs boson was predicted decades before its discovery. Dark matter was inferred from gravitational effects long before anyone knew what it was. Perhaps the particles responsible for the matter asymmetry are hiding in the same way. Not because they are necessarily impossible to detect, but because we are looking for their shadow rather than their body. And there's an even deeper question. Maybe the asymmetry did not originate in the particle physics we normally think about at all. Maybe it began during inflation. Inflation is the hypothesis that the universe underwent an extremely rapid period of expansion in its very early history. During this expansion, quantum fluctuations could have been stretched to cosmic scales. Tiny microscopic fluctuations could become the seeds of galaxies. If inflation happened, it fundamentally changed the way we think about the relationship between microscopic quantum physics and the largest structures in the universe. And it raises another possibility. Could the matter asymmetry have connected to whatever field drove inflation? Some models attempt exactly this. Perhaps the field responsible for inflation interacted with other fields. Perhaps its decay produced an asymmetry. Perhaps the universe's transition from inflation to the hot Big Bang created the conditions required for baryogenesis. We do not know, but the possibilities keep multiplying. And this is the strange feature of the problem. Every serious answer seems to generate another question. If heavy neutrinos created the asymmetry, where did the heavy neutrinos come from? If a new Higgs field created it, why does that field exist? If inflation produced it, what caused inflation? If a deeper symmetry was broken, why did the universe select that particular state? And eventually, every explanation begins to point towards something even more fundamental: the laws themselves. Why do these laws exist?
Why do they permit matter and antimatter to behave almost symmetrically, but not perfectly? Why is CP violation possible? Why are there 3 generations of quarks and leptons? Why does the universe have exactly the particle content we observe? The matter-antimatter mystery therefore sits at a strange intersection. It is a problem about particles, but also about cosmology. It involves quantum mechanics, but also the evolution of the universe. It involves symmetry, but also symmetry breaking. It involves observations made in laboratories, but also events that happened when the universe was less than a second old. And, perhaps most importantly, it asks us to explain something that seems obvious only because it is already here: matter. We are surrounded by it so completely that we rarely question its existence. But if matter and antimatter had been produced in exactly equal amounts, almost all of it could have annihilated. There might have been no stars, no planets, no chemistry, no observers. The universe could have been filled mainly with radiation, and there would be nobody to notice. That means our existence may depend on an asymmetry so small that at first glance it seems almost meaningless. A tiny imbalance, a slight preference, a small violation of a symmetry. And yet, that microscopic difference eventually became the macroscopic universe. But perhaps the strangest part is still ahead, because we have been talking as though matter and antimatter began as equal. That assumption itself needs to be examined. Where did that expectation come from? Why should the universe have started symmetrically in the first place? And what if the deepest mystery is not why matter won, but why the early universe ever gave matter and antimatter an equal starting point at all? To answer that, we have to go further back before atoms, before nuclei, before protons and neutrons, before the familiar forces had fully separated, to an era when temperature and energy were so extreme that our everyday ideas about particles begin to break down. And there, the meaning of matter itself starts to change.
The universe is not simply a box of particles sitting at one temperature. It is a changing environment. The expansion itself can push physical systems away from equilibrium, and this gives a possible opportunity for matter to win. But how? Imagine a heavy particle that can decay in two different ways. One pathway produces matter. The other produces antimatter. If the laws were perfectly symmetric, the two decay rates would be identical. Every decay into matter would be balanced by a corresponding decay into antimatter. Nothing would happen to the overall asymmetry. But suppose CP symmetry is slightly violated. Now the probabilities can differ. Perhaps the particle decays into matter 50.00001% of the time, and into antimatter 49.99999% of the time. The difference looks absurdly small. But now imagine an enormous number of these particles existed in the early universe. That tiny preference could accumulate. And if the particles decay when the universe is out of equilibrium, the resulting asymmetry might survive. This is the basic logic behind many baryogenesis scenarios. The universe does not need a dramatic preference. It needs a persistent microscopic bias, a cosmic thumb on the scale. And this is why CP violation matters so much. CP violation means nature can distinguish certain processes involving matter from their antimatter counterparts. But there is an even deeper symmetry hiding behind all of this. CPT. Charge conjugation, parity, time reversal, combined together. CPT symmetry is one of the deepest structural principles in relativistic quantum field theory. Under CPT, particles become antiparticles, spatial coordinates are reversed, and the direction of time is reversed. For a broad class of well-behaved local Urenson-variant quantum field theories, CPT symmetry is expected to be exact. This has remarkable consequences. Particles and antiparticles must have the same masses. Their lifetimes must correspond appropriately. Their electric charges must be opposite. So matter and antimatter can behave differently in certain processes without violating CPT. That distinction is crucial. CP can be violated, but if CPT holds, the combined transformation remains a symmetry. This means the universe does not simply allow arbitrary matter-antimatter favoritism. The asymmetry has to fit inside a much more constrained mathematical structure. And that makes the mystery sharper. If matter and antimatter can behave differently, what exactly determines the difference? The answer may be hidden in the complex phases of quantum amplitudes. This sounds abstract, but it is central to particle physics. Quantum mechanics does not assign ordinary probabilities directly to every possible outcome. Instead, it uses probability amplitudes. These amplitudes can interfere, and interference depends on phase. Two contributions can reinforce each other, or they can cancel. When different decay pathways contain different complex phases, and when there are also differences arising from interactions and intermediate states, the probabilities for a process and its CP conjugate process can differ. That is one of the mechanisms behind CP violation. So the cosmic imbalance may ultimately depend on something that sounds almost impossibly small. Quantum phases. A phase in an equation, a complex number, a subtle interference effect, and eventually, galaxies. This is one of the most beautiful features of fundamental physics. The enormous structure of the universe can depend on microscopic mathematical details. But the known quark sector does not seem to provide enough of the required effect. So physicists began looking beyond it. One possibility takes us to a scale far above the electroweak energy, grand unified theories. The Standard Model describes the strong, weak, and electromagnetic interactions using separate gauge structures. But perhaps these forces were once different manifestations of a single deeper interaction. At extremely high energies, the distinctions between them could disappear. This is the idea behind grand unification. In some grand unified theories, quarks and leptons are placed into larger mathematical structures. Particles that appear completely unrelated at low energies become different components of a common multiplet. And something extraordinary can happen. Processes that violate baryon number become natural. A quark might transform into a lepton through the exchange of a hypothetical super-heavy gauge boson. If such particles existed in the early universe, their decays could potentially generate a matter-antimatter asymmetry. This is called gut baryogenesis. The idea is attractive because it connects several mysteries at once. Why do quarks and leptons have related properties? Why do the forces appear different today? Why could baryon number be violated? Why is there more matter than antimatter? Perhaps all of these questions are connected to a higher energy unified theory. But there is an enormous problem. The energy scale associated with many grand unified theories is so high that direct production of the relevant particles is completely beyond current accelerators. We may never collide them directly, yet they could have existed naturally in the early universe. The universe itself reached energies that no human machine can reproduce. So once again, cosmology becomes our particle accelerator. But grand unification makes a prediction that is much easier to understand. If baryon number violating processes exist today at an observable level, protons might eventually decay. The proton is stable in the Standard Model as far as ordinary perturbative processes are concerned, but many grand unified theories allow proton decay. Physicists have built enormous underground detectors to search for it. They wait and wait and wait. A proton may survive for more than 10 to the 34 years according to current experimental limits for some decay channels. That is longer than the current age of the universe by an almost absurd factor. Yet if even one proton were observed to decay in a clean, unmistakable way, it would revolutionize particle physics. It would tell us that baryon number is not exact. It could point toward a grand unified theory, and it could connect the physics of today's matter to the events of the early universe. So far, no confirmed proton decay has been found. Again, the universe keeps its secret. But perhaps the most intriguing part of grand unified baryogenesis is that the asymmetry may have been created before the universe even reached the electroweak era. That would place the origin of matter incredibly early. The universe would have started in an environment of almost unimaginable energy. Particles that are completely absent today could have dominated the physics. They could have decayed, their decay products could have become slightly asymmetric, and later, electroweak sphalerons could have reshaped that asymmetry. In this picture, what we call ordinary matter is not the original product. It is the descendant, a remnant of a much hotter and stranger universe.
But there is another problem. Sphalerons can erase certain asymmetries. Suppose an early process creates equal and opposite baryon and lepton asymmetries. Electroweak sphalerons can redistribute them. Depending on the conserved combinations, they can partially convert one into the other. But if the universe creates only a B plus L asymmetry, with B minus L equal to 0, sphalerons can wash it away. This means a successful baryogenesis mechanism has to be more carefully designed than simply create more matter. The asymmetry has to be stored in the right combination of quantum numbers. That is why B minus L becomes so important. If an early universe process creates a non-zero B minus L asymmetry, electroweak sphalerons cannot erase all of it. They can redistribute it between baryons and leptons. A portion can ultimately become the baryon asymmetry we observe. This is one reason leptogenesis is so compelling. A lepton asymmetry can be generated first. Then electroweak processes can partially convert it into a baryon asymmetry. The universe could therefore have started with a difference in leptons rather than baryons. Matter may have won the cosmic competition in a sector we did not originally expect. And that possibility brings us back to neutrinos. There's an elegant connection here.
The seesaw mechanism can explain why neutrino masses are so extraordinarily light compared with other fermions. Imagine that there are very heavy right-handed neutrinos. Their masses could be enormous. Through their interactions with ordinary neutrinos, the resulting mass matrix can produce very small masses for the light neutrinos we observe. The heavier the hidden state, the smaller the ordinary neutrino mass can become. This is the seesaw idea. But those same heavy neutrinos could have another rule. They could decay in the early universe, and if their decays violate CP and lepton number, they could generate a lepton asymmetry. Then sphalerons could convert part of it into baryon number. Suddenly, three mysteries begin to touch each other. Why are neutrino masses so small? Why is there more matter than antimatter? Why might neutrinos behave differently from their own antiparticles? Perhaps they're connected. This does not mean the seesaw mechanism has been proven. It has not. The heavy states have not been observed. The exact mechanism of leptogenesis remains unknown. But the possibility is scientifically powerful because it creates testable consequences. The low-energy neutrino sector could contain clues about high-energy physics. Unfortunately, there is a major obstacle. The CP violation measured in neutrino oscillations may not be the same CP violation responsible for leptogenesis. They could be related in some models, but there is no simple guarantee. A phase measured in a neutrino experiment today does not automatically tell us what happened in the early universe. Still, it gives us something to search for. If neutrinos and antineutrinos oscillate differently, experiments can look for CP violation in the lepton sector. Experiments such as T2K and NOVA have already investigated neutrino oscillations, and future facilities are designed to measure neutrino properties with much greater precision. The hope is not simply to learn more about neutrinos. It is to determine whether the lepton sector contains the kind of asymmetry that could have played a role in creating the universe's matter excess. And if it does, we would still need to connect the low-energy observation to the high-energy cosmic mechanism. That connection would be one of the great achievements of modern physics. But perhaps nature has chosen an even stranger route. Maybe the asymmetry did not come from a heavy particle decay at all. Maybe it emerged from the behavior of a field. Fields can evolve as the universe expands. They can roll down potentials. They can become trapped in metastable states. They can undergo transitions. And if a field interacts differently with particles and antiparticles, its evolution could generate an asymmetry. This opens the door to mechanisms involving axion-like fields, scalar fields, or other hypothetical sectors.
Some models even connect baryogenesis with dark matter, and now the problem becomes enormous. The universe has at least two major mysteries that the standard model does not explain. Why is there more matter than antimatter? What is dark matter? They could be completely unrelated, or they could be two consequences of the same hidden physics. Perhaps the same new particle or field helped create the matter asymmetry and survived as dark matter. Perhaps the dark sector has its own matter-antimatter asymmetry. Perhaps our visible universe is only one part of a larger system. There are models of asymmetric dark matter in which the abundance of dark matter is connected to the visible baryon asymmetry. The idea is tantalizing because the observed densities of visible matter and dark matter are of the same broad cosmological order. That does not prove a connection, but nature often hides relationships between apparently unrelated quantities. And if dark matter and baryonic matter were produced through a common mechanism, the question, why is there more matter than antimatter, could be part of an even larger question, why does the universe contain the particular balance of visible and invisible matter that it does? At this point, the original question has transformed. We began by asking why matter survived. Now we are asking whether the survival of matter is connected to neutrinos, hidden particles, dark matter, grand unification, quantum phases, broken symmetries, and the evolution of the universe itself. And yet there is still a deeper possibility. What if the asymmetry is not merely the result of a new particle? What if it is connected to the very beginning of time? Because if the universe passed through an inflationary era, then the transition from inflation to the hot universe may have been one of the most violent transformations nature has ever produced. Energy stored in a field had to become particles. The universe had to reheat. The resulting particles had to interact, and somewhere inside that process, the difference between matter and antimatter could have emerged. The beginning of the hot universe may therefore have been less like the opening of a curtain and more like a phase transition in which the rules we experience today emerged from a much more symmetric state. And if that is true, then the matter inside your body may be carrying a memory of a symmetry that was broken before there were atoms, before stars, before galaxies, before the universe had anything resembling the structure we recognize today. The next question is almost unavoidable. If the early universe began in a state of extraordinary symmetry, what broke that symmetry, and why did it break in a direction that left matter behind? That is where the mystery becomes even more fundamental. There is a strange point at which the question stops being about particles. At first, it seems simple. Matter exists, antimatter exists. They can annihilate. So why is there more matter? But after following the question backward through particle physics and cosmology, we have discovered that the imbalance may be connected to some of the deepest structures in nature. Symmetry, quantum fields, conservation laws, the expansion of space, the properties of neutrinos, the Higgs field, perhaps even physics beyond the standard model. And yet there is one possibility we have not fully confronted. Maybe the asymmetry was not created because the universe somehow preferred matter. Maybe there was never a fundamental preference for matter at all. Maybe the distinction between matter and antimatter emerged from the particular history of the universe. This is an important difference. The laws of physics may be almost perfectly symmetric, but the state of the universe does not necessarily have to be. A perfectly symmetric law can produce an asymmetric outcome. We see this everywhere in physics. A pencil standing perfectly upright has no preferred direction, but once it falls, it chooses one. A ferromagnet can have microscopic laws that respect rotational symmetry, yet its magnetic moments can align in a particular direction. The laws can remain symmetric while the state becomes asymmetric. This idea is called spontaneous symmetry breaking, and it raises a fascinating possibility. Perhaps the early universe was not born with a tiny instruction saying, "Make more matter." Perhaps it evolved through a sequence of transitions in which a particular state was selected. The difference could have emerged dynamically. But then we must ask, what selected that state? Was it quantum fluctuations? Was it a field configuration? Was it a phase transition? Was it the decay of an unknown particle? Or was it something even deeper? At this point, physics reaches a boundary where different possibilities compete. Some mechanisms can be tested in laboratories, others may be accessible only indirectly, and some may remain beyond our experimental reach. That is why the matter-antimatter problem is not merely an unanswered question. It is a map pointing toward missing physics. The standard model is not a failure. Quite the opposite. It is one of the most successful scientific theories ever constructed. It correctly describes 3 of the 4 known fundamental interactions at the quantum level. It predicted the Higgs boson. It explains the behavior of quarks and leptons. It survived experiment after experiment. But it leaves several major questions unanswered. It does not explain dark matter. It does not incorporate gravity into the same quantum framework. It does not explain the observed pattern of neutrino masses. And it does not naturally produce enough baryon asymmetry to account for the matter-dominated universe. That last problem is especially interesting because the universe itself is the evidence. We do not need to build a machine capable of reproducing the earliest moments of cosmic history. The experiment has already happened. The result is everywhere. The galaxies are the result. The stars are the result. The Earth is the result. We are the result. The matter asymmetry is not some tiny correction hidden in a laboratory measurement. It is written into the existence of the visible universe. And perhaps this gives us a different way of thinking about scientific evidence. Sometimes the most important clues are not unusual objects. Sometimes the clue is the fact that everything exists in the first place. Look at your hand. It appears ordinary. Atoms arranged into molecules, molecules arranged into cells, cells arranged into a living organism, but every proton in that hand may be part of the tiny surplus left over from an almost complete matter-antimatter annihilation billions of years ago. The carbon in your body was forged inside ancient stars. The hydrogen was mostly created in the early universe. The particles themselves emerged from quantum fields, and the fact that those particles are still here may ultimately trace back to an asymmetry created when the universe was unimaginably young. That means your existence depends on an event you cannot see, an event that happened before Earth existed, before the Sun existed, before the Milky Way had its present structure, before there were atoms, and perhaps before the forces of nature had the forms we recognize today. There is another subtle point. The matter in the universe is not merely extra, it is structured. The asymmetry allowed stable nuclei to exist. Those nuclei allowed atoms to form. Atoms allowed chemistry. Chemistry allowed stars, planets, oceans, and eventually life. The asymmetry did not directly create complexity, but without surviving matter, there would have been nothing from which complexity could develop. A tiny imbalance became the raw material of cosmic history. And this makes the number itself almost absurd. The excess is tiny compared to the enormous amount of energy that once filled the universe. Almost all of the original matter and antimatter annihilated. What remained was only a tiny difference. It's as though the visible universe is the residue left after an enormous cancellation. Imagine writing two enormous numbers on a page. Each contains a billion particles. Then subtract almost everything. The result is tiny compared to the original numbers, but that tiny remainder is what matters. Cosmically speaking, we may be living inside the remainder. There is even a more beautiful connection here. The photons produced during the annihilation of matter and antimatter did not disappear. They remained part of the universe's radiation. As the universe expanded, that radiation cooled. Eventually, some of it became the cosmic microwave background we observe today. So the universe may contain two kinds of evidence from the same ancient story. The radiation remembers the hot early universe, and the matter around us remembers the tiny imbalance that survived it. One is the echo, the other is the residue. Together, they tell us that the young universe was extraordinarily different from the one we inhabit now. But can we determine exactly which mechanism produced the asymmetry? Not yet. That distinction matters. There's a temptation in popular explanations to say, neutrinos caused it, or CP violation caused it, or grand unified particles caused it. But science does not currently know that. These are possibilities. Leptogenesis is a serious theoretical framework. Electroweak baryogenesis is a serious theoretical framework. Grand unified baryogenesis is another. There are other mechanisms as well. Some may eventually be ruled out, some may survive. Some may lead to entirely new predictions, and perhaps an experiment we have not yet imagined will reveal the missing clue. This is where the search becomes exciting. Physicists are not simply sitting and waiting for a perfect theory to appear. They are looking for evidence. Neutrino experiments are measuring oscillations and searching for CP violation. Large underground detectors are searching for proton decay. Collider experiments continue to test the Higgs boson and search for new particles. Cosmologists measure the cosmic microwave background with extraordinary precision. Astronomers measure the distribution of matter across enormous distances. Nuclear physicists search for neutrinoless double beta decay. Each experiment attacks a different part of the mystery, and perhaps one of them will eventually reveal the missing piece. Imagine, for example, that a future experiment discovers neutrinoless double beta decay. That would tell us that lepton number is not an exact symmetry and that neutrinos have Majorana character. It would not automatically prove leptogenesis, but it would dramatically strengthen the possibility that neutrino physics is connected to the origin of matter. Or imagine that a future collider discovers a new particle interacting with the Higgs field. If its properties allow a strong electroweak phase transition and new CP violation, electroweak baryogenesis could become much more plausible. Or imagine that proton decay is finally observed. That would immediately tell us that baryon number is not exact and could provide evidence for a much deeper unified theory. Or imagine that none of these things happen. That would be important too. The theory that repeatedly predicts observable effects that never appear becomes increasingly difficult to defend. Science advances not only through discoveries, it advances by eliminating possibilities. And perhaps the most profound possibility is that the answer will come from somewhere we have not been looking. This has happened before. The discovery of neutrino oscillations showed that the Standard Model in its original form was incomplete. The discovery of dark energy showed that our understanding of cosmic expansion was incomplete. The discovery of the Higgs boson confirmed one enormous part of the Standard Model, while leaving other mysteries untouched.
Nature has repeatedly shown that the next layer is stranger than the previous one. So perhaps the matter-antimatter imbalance is not an isolated problem. Perhaps it is the first visible crack in a deeper theory. A theory that might explain why there are 3 generations of particles, why neutrinos are so light, why the forces have the strengths they do, why the Higgs field has its particular properties, why dark matter exists, why gravity is so different from the other forces, and perhaps eventually why the universe has the particular structure that allows matter to exist at all. But there is a limit to how far we can currently go. We can trace the story backward to an extremely hot early universe. We can describe the particles and fields that existed at different stages. We can calculate how asymmetries might develop. We can measure the matter density of the universe. We can test CP violation. We can search for new particles. But we cannot yet point to one confirmed mechanism and say, this is why matter survived. The answer remains open. And perhaps that is more beautiful than a simple ending. Because science is not a collection of finished answers. Sometimes its greatest achievements are the questions it manages to formulate precisely. For centuries, humans could look at the stars without knowing what they were made of. Then spectroscopy revealed that stars contain the same chemical elements found on Earth. For decades, the atomic nucleus seemed fundamental. Then quarks emerged. For years, neutrinos seemed massless. Then oscillations showed otherwise. And now we know that the ordinary matter around us may itself be the leftover consequence of an asymmetry whose origin remains hidden. The mystery has become precise. That is progress. We know what needs to be explained. We know roughly how large the asymmetry is. We know the conditions that a successful mechanism must satisfy. We know several candidate mechanisms. We know which parts of the Standard Model are insufficient. And we know where to look for clues. But there is one final shift in perspective. When we ask why there is more matter than antimatter, we often imagine that the answer should explain the existence of matter. But perhaps it should explain something more subtle. Why was there an imbalance at all? Why did the universe fail to cancel perfectly? Why did one side survive by such a tiny amount? Why did the equations permit the possibility? Why did the early universe pass through the conditions necessary to preserve it? And why did the final remainder become a universe capable of forming stars, planets, chemistry, and observers? We do not know, but we can say something remarkable. If the asymmetry had been exactly zero, there probably would be no ordinary matter-dominated universe like the one we know.
If the asymmetry had been dramatically larger, the universe could also have evolved very differently. The actual value appears to sit in a narrow story of cosmic history. A tiny imbalance, not enough to overwhelm the universe. Not zero, just enough. Enough matter survived. Enough structure formed. Enough stars ignited. Enough planets assembled. And eventually, enough complexity emerged for the universe to ask the question itself. Why is there more matter than antimatter? There is something almost circular about that. The universe produced an imbalance. The imbalance produced matter. Matter produced stars. Stars produced heavier elements. Those elements produced planets. On at least one planet, chemistry became biology. And eventually, biology became capable of building instruments that could study the particles left over from the beginning. We are not outside this story. We are part of its consequence. Every proton in your body carries baryon number. Every atom around you is part of the surviving matter. And every star you see is made from the same cosmic remainder. The question began in particle physics, but the answer, whatever it turns out to be, is written across the entire universe. Perhaps the next great discovery will come from a particle accelerator. Perhaps from a neutrino detector buried beneath a mountain. Perhaps from a detector waiting patiently for a proton to decay. Perhaps from the sky. Or perhaps from a theory that changes our understanding of what matter, symmetry, and even the early universe really mean. For now, we stand at the edge of the known. We know that matter exists. We know antimatter exists. We know their laws are almost symmetric. We know the symmetry is not perfect. We know the early universe was hot and dense. We know the visible universe contains a tiny excess of matter. And we know the physics we currently possess does not yet fully explain that excess. Somewhere between those facts lies the missing piece. It may be hidden in a particle we have never seen, a field we have never detected, a symmetry we have not yet understood, a process that occurred only once, billions of years ago. Or perhaps in a deeper law from which our present laws are only an approximation. And until we find it, one of the most ordinary things in existence remains one of the greatest mysteries: matter. The substance of stars, the substance of planets, the substance of you. All of it may be here because in the earliest moments of the universe, matter and antimatter did not cancel perfectly. Something survived. A tiny excess, a microscopic difference, a barely perceptible departure from perfect symmetry. And from that almost nothing came almost everything.